Oh, really?
Okay, well, I guess we'll get started. It looks like we have everybody here. What we're going to talk about this morning is the Belimo energy valve. Now, the energy valve is a pressure-independent valve. So the way I start the class is I start by going through some pressure-independent valve information, and then we get to talking a little bit more about the energy valve in particular. So this is just a graphic showing a 2 to 10 volt control signal. And you're probably guessing what I'm getting to here. You've probably all seen it before, that nice little football-shaped graphic. But what we're looking at is, this is our coil output curve. Then, as we've probably all seen in the past, we want an equal percentage flow characteristic out of our valve so that our final coil output is linear. So what that means is, at half our signal, we're going to be getting half of our coil output. This graph here is from an independent study we had done at a place called the Iowa Energy Center, part of Iowa State University. We had this done when we first brought out our PICCV, our smaller pressure independent valves. This is looking at a pressure dependent valve, and we're going to look at what happens at different differential pressures across the valve. Typical 5-pound differential, see we're at maybe 1.2 GPM. Bump that up to a 10 psi differential. You can see our flow in our pressure dependent valve, we were looking at a glow valve, goes up to maybe 1.7. So you're talking half a GPM difference. And that's what this little waste zone, as we call it, represents. Well, you may think, what's half a GPM? Well, typically, especially when we're talking about the smaller pressure independent valves, you could have a couple hundred of these on the job. So once you start talking about a couple hundred times half a GPM, you can see where you're wasting pump energy by pumping all this extra water. Now we're going to look at the same type of graphic, but with a pressure independent valve. So you can see here now, with this graphic, the scaling is different. So just so we can show that there is a small waste zone, but it's much smaller than the pressure dependent. So between that 5 and 10 pound change in differential, we have maybe 1/10 of a gallon change in flow. So obviously a much smaller waste zone using pressure dependent valves. Now again, this is from the same study, the Iowa Energy Center. And what we're looking at here is the time sequence, and over on the right here, we're looking at the pressure dependent valve and all the changes that are made to achieve the necessary space temp. Now on the left, what we're showing is the pressure independent valve in comparison to the pressure dependent valve. We'll overlay these two, and you can see the swings in blue from the pressure dependent valve are all over the place. And I've heard some people say, well, it's going to balance out, the overflow up here versus the underflow. It doesn't. It seems like that would be the case, but we've done studies on it, looked at these things, and they do not balance out. You end up having net overflow when you're looking at this. Now looking at the cost of operating the waste zone, so using a bunch of pressure dependent valves. Here we've got 180 ton load. We've got a couple different chillers. We've got one chiller loaded up at 90%. Each chiller can handle 200 tons, so we've got a 180 ton load. We're good. The flow in the loop is 360 GPM. Our design delta T is 12 degrees at 360 GPM. Like I said, we've got the one chiller loaded at 90%. Now what's going to happen if we start seeing some low delta T, we drop down to 10.4 degrees because our flow has increased to 414 GPM. Notice though that the load has remained the same. However, we're requiring more flow to meet that same load. Well, as you can see, what's going to happen is because each chiller can handle 200 tons, we actually have to bring on a second chiller, not because our load's changed, but because the amount of water we're flowing through has gone up to 414 GPM, and each chiller can only handle 400 GPM. Or, I'm sorry, 200 GPM. So what we're saying there is that you have to run your central plant to supply the building's need for water, not its need for cooling. And what we're getting at is that, you know, you're bringing on this additional chiller not because of anything that's required from the load, just because of the additional flow that's being pushed around the building. Pressure independent valves are two-way valves, and they're two-way because you have to be able to sense inlet and outlet pressure. And they're pressure independent regardless of pressure variations in the system. So you're going to maintain a constant flow for each position of your control valve. Control signal. I'm sorry. Yep, control signal, which is of course going to position the valve in a certain place each time.
Say it again, please. You're going to achieve what now?
You're going to get a specific flow for each value of your control signal. So say you're at 6 volts. So over a 10 volt range, that's 50%. You're going to get 50% of the rated flow of that valve whenever you're at 6 volts. Now in comparison to a pressure dependent valve, if you have that valve at 6 volts, you're not going to always get that same flow rate because, for example, say you've got a loop with 10 valves in it. Say 8 of those valves close off and you get a spike in your pressure on the last 2, you're going to get a spike in flow with that spike in pressure until you get a temperature change in the room that the building automation system will notice, and then it will back off on that valve. So and then you're not going to be at 6 volts anymore. Your automation system is going to say, oh, we don't need as much flow anymore, so bring it back to 4 volts, 3 volts, whatever the case may be.
But when the pressure spikes, isn't the pump going to back off?
Eventually it will. It's not instantaneous.
Right.
Oh, okay. You're saying instantaneously this is
This
what's
valve, it's instantaneous. Yes. Yeah. A couple different formulas here that I'm sure y'all already know. But the CV formula, GPM divided by your square root of your delta P, that goes away with pressure independent valves because we're not worried about the differential pressure anymore. So you size up pressure independent valves based on your flow. Now I say we don't worry about the differential pressure. We do in some regard. We want the pressure to be between 5 and 50 psi across your pressure independent valve to maintain the pressure independence. If you're outside of those ranges, the valve will still work, but then it'll start working like a pressure dependent valve in that you will see differences based on pressure fluctuations.
And that's more true in a mechanical pressure independent valve than an electronic pressure independent valve.
Right.
Which
Right.
one is this?
The energy valve that we're going to be talking about is an electronic, so you don't see that as much. We can actually be pressure independent down to 1 psi on the electronic pressure independent valves. And then our power output, the main thing to get out of here is that, just to be aware that flow and delta T are inversely proportional. So as your flow increases, your delta T is going to decrease, and that's going to lead to that low delta T syndrome that you hear about. Overpumping. So we've been talking that, with pressure-dependent valves, you're susceptible to overpumping. Well, what's that going to do? Well, you can see here our coil characteristic, our valve characteristic, and then your delta T. You can see your delta T is coming down, as we talked about, as your flow increases. Well, it's going to create a waste zone, because what you ended up with is your power saturation point is right here. What the power saturation point is, that's the point where you've basically maxed out your coil. So beyond that point, any additional flow through the coil, you're not going to achieve any additional output capacity, or very little. So that's why we call it the waste zone. Power saturation point, our definitions, point beyond which coil cannot yield additional heat transfer regardless of increased flow, and then the waste zone, obviously from this graph, the range beyond the power saturation. Now we'll talk a little bit about the energy valve, and we have the energy valve in a couple different sizes. I brought the small one just so I wouldn't break my back. It'll look like this in the 1/2 through 2 inch models. Our 2.5 through 6 inch are flanged. Now, in the folders that we've handed out here, open one up so I can just mention a little bit what we have. On the left side of the folder, everything there is related to the energy valve. On the right side, that's all about just pressure-independent valves themselves, and then I have just a general product overview at the back of that. Some of the literature that we have in here, I'll reference in the presentation. Some is just for your knowledge to look over whenever you have time. We have case studies in there, white papers, things like that. So what is the energy valve? Why is it different from a standard pressure-independent valve, from a pressure-dependent valve? Well, like I said, it is a pressure-independent valve. It is one where we can measure energy, control power, and manage the delta T. So you can see here, this is the large version. I see why I don't carry that around with me. Before we brought the small one out, that was all I had, so I did lug that around. Well, as we were saying, we can measure the energy with these valves, control power, manage delta T, and you basically have an integrated BTU meter. Now, I've been told by some contractors that using this valve costs less than some of the BTU meters that are on the market. I've had people tell me that they're not even using the valve for all its functionality. They buy it as a BTU meter at times. We recommend, of course, that you use the valve to its full capabilities, but I just wanted to put that out there that it is a nice BTU meter as well. So what is the valve made up of? First, we have the valve body. It's a characterized ball valve, a Belimo smart actuator. On the large ones, we have a magnetic flow sensor. On the small, it's an ultrasonic flow sensor. We have 2 temperature sensors. With the larger valve, as you can see here, one of the sensors is embedded in the valve body. The other would be mounted on the opposite side of your coil. With the small, we have these 2 pieces of pipe. That's where the sensors are embedded. Again, one would be mounted on the supply, one would be mounted on the return side of the coil. And then the valve also has backnet built in, MSTP or IP. So with this product, we're able to measure flow and delta T, which allows us to measure, observe, record, and trend performance data. All that can be sent back to your automation system via BACnet. And you can see on the back of the actuator here, we have a plug where you can plug in your Cat 5 cable. Now you can also just bring your laptop up and connect the Cat 5 cable right to the valve itself. If you don't have a Cat 5 drop near where the valve is going to be, which does happen quite often, if you want to read the information off the valve, just bring your laptop, Cat 5 cable, plug in the IP address, and you can read the information right there. So, because we're able to measure flow and delta T, that allows us to directly control based on your flow or your energy. So what are we saying here? Well, when we're talking about the flow, the valve will get its control signal from your building automation system, as usual. It sees that control signal as a request for a certain amount of flow, a certain amount of GPM. Then the sensor can sense if, for example, some other valves close, it gets an increase in pressure. The sensor will identify an increase in flow starting, and then it will adjust the valve position so you maintain the same flow because you haven't changed your control signal at all. It's just an increase in pressure or decrease in pressure, either way, that's caused a change in what the sensor is seeing. Now on the energy side of things, the energy valve basically becomes one with the coil in that it knows the max BTU output of the coil. And so, and this is the part that I haven't done as much, so if I say something wrong, Brian, jump right in. But basically what we're trying to do is control to the energy requirements of the room. So if it requires X amount of energy and we know the coil can do 2X, then the valve will get a 50% control signal, or it'll control to 50%, I should say, of that BTU requirement.
So basically your control signal controls the BTU of GPM. That's what that means.
And the valve is constantly, adjusting
In that
at the
case,
same control signal to maintain.
It'd still be pressure dependent, but we're looking for a BTU output rather than a GPM output. So 0 to 100,000 BTU on a 2% signal. The 6 volts would give you 50,000 BTUs output. It's used a lot for like surgery suites, museums, libraries, places where it's critical control. So you'll see that a lot more there. It's a lot more applicable.
Because you're factoring in temperature too, not just flow, right?
Yeah, when you're using that formula he showed earlier, Q is 500 times GPM times your delta T to get your actual power.
But this is the standard energy valve.
It's a standard feature of the energy valve.
Right, well,
But basically, I guess let's step back here a little bit. You can turn delta T on and off, the delta T manager that he's talking about, and you can turn
Oh.
this power control on and off. You can also, I don't know if you have these slides in there, but you can set this valve up as pressure dependent or pressure independent.
Yeah, at the end I've got
You got this, I'm stealing some thunder, but at the end I'll get up if I think there's nothing.
but if it's pressure independent, it's controlling on flow or it's controlling on BTUs?
It's controlling 2 BTUs, but it also knows what the flow is. So it
Yeah.
makes that formula Q equals 500 times your GPM.
Right.
So as that GPM changes, it's just looking at that whole equation to get the Q or the BTU out.
All right, so it's never controlling on flow. I'm just trying to make sure I have it clear how it works.
If it was not operating in power control, just operating as a standard, what we call flow control, then yes.
Okay, you can set it up either way.
Yes.
This thing can be set up in about, I think there's about 12 different modes when you mix and match ons and offs. So it's a really smart valve. It's got a lot of features in it, but you can turn them all off, and you can buy this valve, put it in its pressure dependent.
Yeah.
So I can put it in as pressure independent, controlling on flow. I can put it in as pressure independent, controlling on BTU.
Correct?
Right.
I mean, like when I buy the energy valve, I get the temperature sensors, and I mean, you know, that's all comes with it.
It
You
does.
get it all, but you can use it as just a standard ball valve.
Right.
All the way
Which
up
we'll
to-
talk about, about why you might want to do that. Why am I going to spend all this money on all this, you know, extra goodies and run it as a pressure dependent valve? We'll talk about why you might want to do that. But yeah, this is the formula that Brian was referencing, the power output formula, and that's why we're still using the GPM and the delta T, even when we're talking about controlling based on power requirements. So here we're looking at measuring the delta T, and the way we can do that is because we have the temperature sensors built in there. And you can see here, we've got our coil output, so that's the power of our coil, and we've got our delta T coming down here. Now, up at the top here, the power saturation point, which on this graph, I think they marked it a little early, but really the power saturation point is when that curve flattens out. Because that's when you're not getting any more heat transfer out of your coil. When that happens, that's where you should set your delta T. So, as Brian was mentioning with the delta T manager, that's one of the settings that's in the valve. You can say, this is the delta T I want to achieve. The valve, once it sees you're at that delta T, if you drop below it, the valve will take over from the building automation system and say, we're not going to allow any more flow through this coil, because that, as we talked about in the other formula earlier, the delta T and flow are inversely proportional. So more flow will cause more of a decrease in delta T. We won't allow that to happen. I was thinking there was another slide after this, and we've got a few different presentations on this product, but the one slide that I'd like to see that's not in this presentation, we draw a line down